Sample problem 18.5 still deals with some qualitative aspects of acid-base equilibria, but starts bringing some numbers into things. So remember, when we have these kinds of acid-base equilibria, they're equilibria, and we can have chemistry happen such that the equilibrium will lie on one side or the other of the equation, of the equilibrium. So we need to be able to evaluate, and that's what this problem asks us, predict the net direction and whether Kc is greater than or less than 1 for each of the following reactions. And we're going to assume that we have equal starting amounts of each species, but we need to ask that once this chemical reaction reaches equilibrium, where does the equilibrium lie? Remembering that if the equilibrium lies on the reactant side, Kc is going to be less than 1. If the equilibrium lies on the product side, Kc will be greater than 1. And some people got a little bit confused when we did this problem. Why are we dealing with Kc's again? I thought this chapter was all about acids and bases and Ka's and Kb's. But remember, if we have acids and bases reacting, each of those have a Ka or a Kb value that talks about how tightly those species hold on to their protons. But this is really a chemistry. You can think about Kc here being a chemistry, that we need to think about when this chemistry happens, where do we end up at the end of the day? And so what we really need to do here is we need to evaluate who's the stronger acids or stronger bases. So this kind of ties in parts of our previous sample problem, which asks us to identify conjugate acids and bases. And the rule here is, and remember, we've seen this time and time again, chemistry happens to make species that are lower in energy, less reactive. So we are going to lie on the side of the equilibrium that has weaker acids and weaker bases. Okay, so let's work through a sample problem to see if we can make sense out of this. So let's take this first reaction, H2PO4 minus plus NH3 generates NH4 plus and HPO4 minus. So the first thing that we need to do is figure out who's the acids and who's the bases. So this kind of brings in information from sample problem 18.4, where we need to see that these two are related and these two are related. So again, this guy gives up a proton, so this must be the acid here. So here's the conjugate base. And then this guy over here must be behaving as a base, because you're never going to have two acids react. An acid is going to give up a proton to a base, and that base then will become the conjugate acid. So that was kind of what we had to do in sample problem 18.4. What we need to do now is look at this chemical equilibrium and say, which side of the equilibrium do we lie on? And to answer that question, we basically just need to ask a follow-up question and say, who is the weaker acid? And so we're going to compare acids. So here essentially are our two acids. We have a molecule that's an acid on the right side of the equation, because remember, we could write this equilibrium going the other direction, in which this guy would be an acid making this conjugate base. So we need to look at these acids and we need to say, who's the weaker acid? The equilibrium will lie on the side of the weaker acid. So the equilibrium lies on the side of the weaker acid. And that's the whole rule. So a couple of things to show you here. There's a sheet that we handed out in class that basically shows some of our common acids and bases, and it just kind of shows them in a hierarchy of very weak to our strong acids. So for this problem, we're actually going to be able to use this sheet, and we can find H2PO4 minus, which is right here, and then we can find NH4 plus, which is right here. We can see that NH4 plus is a weaker acid than H2PO4. So this guy is again the weaker acid. That means the equilibrium lies here. If the equilibrium lies on the right side of the equation, that means that Kc is going to be greater than 1. We're product heavy. Okay? If that's still fuzzy in your head, we need to make sure that you go back to chapter 17 and understand, large equilibrium constants means that we're product favored. And we compared these two acids to say we are going to lie on the side of the weaker acid because chemistry will have happened. And lying on the product side means Kc is greater than 1. So again, this is a nice sheet to kind of do this very easily in this regard. But one of the things that you want to be familiar with and what you will get for the exam and the quiz is a copy of Appendix C. So this is Appendix C from the back of your textbook. And it lists a whole bunch of different acid species, and it lists their equilibrium constants, their Ka values. Okay, so we have a whole bunch of them that are listed here. We'll get to in a little bit why there's Ka1, A2, and A3 for some species and not for others. But you might not be given a ranked hierarchical list. You might rather be given actual equilibrium constant data. In that case, we have to remember that weak acids are going to have small Ka values, whereas strong acids are going to have large Ka values. So in that case, this problem just becomes a little bit more complicated, where you've actually got to look up the species on this table and then look at their Ka values. Okay? But for right now, we'll just keep it simple with this sheet. So let's go a little bit more quickly then through our second example here. We've got H2O plus HS generating OH minus plus H2S. We've got to match up the species that are acids and conjugate bases, or bases and conjugate acids. So this is an acid. Water in this case is going to be our acid, making hydroxide as the conjugate base. We've got HS minus as our base, generating H2S as our conjugate acid. So in this case, again, we need to compare our two acids. We need to look at H2S versus H2O. So I'm going to grab this here. Here's H2O, and here's H2S. Okay? H2O is a weaker acid than H2S, right? Acid strength is increasing here. H2O is a weaker acid. Our equilibrium lies on the side of the weaker acids. So our equilibrium is going to lie on this side. Lying on the reactant side, again, means Kc is going to be less than 1, a smaller number. So again, this problem got a little bit confusing for some people because we actually were thinking about Ka values for individual acid species. And those allow us to determine for this chemistry which side the equilibrium lies on, and then we could figure out a Kc in terms of greater than or less than 1 for the overall reaction.